Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to start exploring thermochemistry, which is part of the broader field of thermodynamics. Thermodynamics is the study of heat transfer, and thermochemistry is specifically the study of heat transfer in chemical reactions. In order for us to discuss thermochemistry, we need to first cover energy. Energy is the essence of our very existence as individuals and as a society. The food that we eat gives us the energy to live, work, and play, just as the oil consumed by manufacturing and transportation systems power our modern industrialized civilization. And while the concept of energy is quite familiar, energy itself is rather difficult to define precisely. In our lecture today, we're going to define energy as the capacity to do work or to produce heat. One of the most important characteristics of energy is that it is conserved. The law of conservation of energy states that energy can be converted from one form to another, but it can be neither created nor destroyed. That is, the energy of the universe is constant. Now let's talk about the different types of energy we might encounter. We can divide all energy into two broad categories: kinetic energy and potential energy. Potential energy is energy due to position or composition. Various types of potential energy include gravitational potential energy. This is energy stored by objects due to their position above Earth's surface. Then there's elastic potential energy. This is energy stored when objects are stretched or compressed. Nuclear potential energy is energy that's contained within the bonds that hold the nucleus together. And chemical potential energy is energy stored in chemical bonds between atoms and molecules. Then the kinetic energy of an object, this is due to the motion of the object. Various types of kinetic energy include motion kinetic energy. This is the energy of an object in motion, and it's directly observable as mechanical movement. Sound energy is the energy carried by sound waves, which is a form of mechanical energy through a medium. Thermal energy is the collective energy of particles moving within a substance, contributing to its temperature. And finally, electrical energy is energy carried by moving electric charges, often electrons, through a conductor. With this understanding of what energy is and how it exists in different forms, it's important to pause and go over terminology that's going to reappear in this lecture for this unit before we dive any further. First and foremost, in thermochemistry, it's important to distinguish between the system and the surroundings. When we discuss reactions, we divide the universe into two parts: the system and the surroundings. The system is the part we're focused on, usually the reactants and products in a chemical reaction. The surroundings are everything else: the beaker, the room, the air, the lab equipment, so on and so forth. Understanding this boundary is important because energy flows between the system and its surroundings. For example, if a reaction releases heat, the system is losing energy and the surroundings are gaining it. Further, we can also classify systems based on how much interaction they have with their surroundings. For example, an isolated system can't exchange matter or energy with the outside world, with the surrounding. Think of an insulated, sealed container. Nothing gets in and nothing gets out. This is in comparison to a closed system, which can exchange energy but not matter. And this is common in many lab setups. Finally, an open system can exchange both matter and energy. So take as an example a boiling pot of water on a stove. Steam escapes into the air. Both energy and matter are being exchanged because the pot is open to the surroundings. Now, as we start thinking about how to describe these systems, we also need to be precise about the properties we use to define them. Properties fall into two main categories: intensive properties and extensive properties. Intensive properties do not depend on how much material you have. For example, the temperature of a glass of water doesn't change if you pour it into a larger cup. So things like temperature, pressure, and density, they all stay the same regardless of sample size. In contrast, extensive properties do depend on the amount of substance. These include volume, mass, number of moles, and energy. If you change the amount of substance, these values will change too. Finally, we want to discuss the difference between state functions and path functions. A state function is a property that depends only on the initial and final state of the system, not the process used to get there. So think of it like elevation. If you hike from the base camp to the top of a mountain, the change in elevation is the same, whether you take the steep trail or the winding one. In thermodynamics, common state functions include enthalpy, Gibbs free energy, internal energy, and entropy. For these values, for these state functions, we calculate them as final minus initial. In contrast, a path function depends on the specific route taken. Values that are path functions include work and heat. The total amount of work done or heat transferred can vary depending on how the process occurs, just like a longer trail takes more energy to hike. Now that we've covered some important terminology, let's return to the concept of energy within a system, specifically its internal energy, which we're going to denote as U. The internal energy of a system is the total amount of kinetic and potential energy contained within all its particles. This includes the vibrations, rotations, and interactions of atoms and molecules. In other words, all forms of microscopic energy. Now, while we can't measure the exact value of internal energy, we can measure how it changes. And the change is what we refer to as delta U. Delta U tells us how much internal energy the system has gained or lost as it undergoes some process. If delta U is negative, that means that the system loses energy. Energy has flowed out of the system. On the other hand, if delta U is positive, then the system has gained energy. Energy has flowed into the system. This idea leads us into one of the fundamental principles of thermodynamics, the first law, also known as the law of conservation of energy. It tells us that energy can be transferred or transformed, but it cannot be created or destroyed. That means that any energy lost by the system must have gone into the surroundings. And any energy gained by the system must have come from somewhere, the surroundings. We can express this idea mathematically with the following relationship. The change in the internal energy of the system is equal to the negative change in internal energy of the surroundings. So this equation reminds us that the total energy between the system and surroundings stays constant. Energy doesn't disappear, it just shifts between system and surroundings. So now that we know energy cannot be created or destroyed, we want to ask, how does it actually move? Energy can be transferred in two main ways, as heat or as work. And this gives us a really important equation. The change in internal energy is equal to heat plus work. This formula expresses that the change in internal energy, again, equals the heat added to the system plus the work done on the system. And what we're going to do next is break down both of these components, starting off with heat, which is symbolized as lowercase q. Heat is the flow of energy that happens because there's a temperature difference between two things. Energy will always flow from hot to cold, never the other way around. So if you drop an ice cube into hot coffee, the heat flows from the coffee into the ice, not the other way around. Here it's important to clarify two common misconceptions. Heat is not the same as temperature. Temperature measures the average kinetic energy of particles in a substance. Heat, on the other hand, is energy in transit. It flows as a result of temperature differences. Further, heat is not energy itself. Rather, it's one of the two main mechanisms through which energy is transferred. The other mechanism is work, which is symbolized with a lowercase w. Work is energy transfer that occurs when a force causes an object to move. We define it in the following way. Work is equal to force times distance. In thermodynamics, especially in the context of gases, we often encounter pressure volume work, where the gases expand or compress against a pressure. And that leads us to a more common equation for work. Work is equal to negative pressure multiplied by the change in volume. Then when we're dealing with reactions involving gases, we can also express this in terms of moles of gas. So you can get the relationship that work is equal to negative change in the number of moles of gas multiplied by the ideal gas constant multiplied by temperature. And we get this equation as a consequence of negative P multiplied by delta V. Delta V can be expressed as nRT, change in nRT divided by pressure. And if we go ahead and replace the delta V term with this, we'll notice that the pressure terms cancel out and we get negative delta N for the number of moles changed for gases multiplied by RT. So this is where that version of the equation comes from. Now, whenever we deal with heat and work, we have to be really careful with signs. In chemical thermodynamics, we always view things from the perspective of the system. So the sign conventions look like this. For heat, if heat is added to the system, then Q will be positive. If heat is removed or lost by the system, then Q is going to be negative. For work, if the surroundings do work on the system, then W is positive. But if the system does work on the surroundings, then W is negative. So for example, if a gas expands, then it pushes against a piston, it's going to be doing work on the surroundings. So W is negative. But if we compress the gas, then you're doing work on it, so W is positive. Keeping track of these signs is going to be important, not only in this lecture, but all of the videos that are going to follow that discuss thermochemistry, because it helps us correctly determine whether the system is gaining or losing energy overall. And since we're going to be using our equation, delta U is equal to Q plus W a lot moving forward, you'll want to make these sign rules second nature. And the best way to do that is to tackle a couple of practice problems. This first problem says, which of the following statements is correct? Let's go through each option one by one and figure this out. A says volume is a path function and an intensive property. This is incorrect. Volume is a state function. A state function depends only on the current state of the system and not on the path taken to get there. Volume fits this definition because it reflects the amount of space a system occupies at a given moment, and that value depends only on the system's current pressure, temperature, and number of moles, and not how the system got to that volume. In addition, it's an extensive property, not an intensive property, because the volume of a system increases if you have more substance. B says free energy is a path function and an intensive property. This is also incorrect. Free energy, specifically Gibbs free energy, so delta G, this is a state function, not a path function. It reflects the energy available to do work, and it depends only on the current state of the system. Further, it's an extensive property because it scales with the amount of material. C says internal energy is a state function and an extensive property. This one is correct. Internal energy is a state function because it only depends on the system state, not the path taken to get there. And it's extensive because it depends on the total amount of substance. If you double the system, you double the internal energy. So C is the correct answer for this first problem, but let's still work through D. D says that pressure is a path function and an extensive property. This is incorrect on both counts. Pressure is an intensive property, and it's also a state function, not a path function. So the correct answer here is C. Problem 2 says, which of the following statements is correct? From a quick glance, we're being asked to evaluate 3 statements about heat and work. So let's take them one at a time and think about them from the system's perspective, which is the standard convention in thermochemistry. Statement 1 says, increasing the heat of surroundings produces a negative Q. This is true. If the surroundings are gaining heat, then the system must be losing it. And since Q represents heat from the perspective of the system, a loss of heat means a negative Q. Statement 2 says, increasing the work done on the surroundings produces a negative W. This is also true. If the system is doing work on the surroundings, for example, if a gas expands and pushes against a piston, the system is losing energy. That means that work is going to be negative. Finally, statement 3 says, when heat is added to a system, its sign is negative. This one is false. When the system gains heat, meaning heat is added to it, Q is going to be positive. So that's why this statement is incorrect. Since only statements 1 and 2 are true, the correct answer is A. The next problem says, which of the following statements is true about internal energy and the first law of thermodynamics? Statement 1 says in an isolated system, the internal energy is constant. This is true. An isolated system, remember, it can't exchange heat or work with its surroundings, so no energy comes in or out. Delta U, therefore, is going to be 0. Statement 2 says work done on a system decreases its internal energy. This one is false. Work done on a system increases its internal energy. It's like giving the system energy. Then finally, statement 3 says the change in internal energy is equal to the heat added plus the work done on the system. This is exactly what the equation we covered earlier states. So this one is true. Once again, change in internal energy is equal to heat plus work. So since statements 1 and 3 are true, the correct answer is B. Finally, our last problem says, when a system releases 180 joules of heat to its surroundings, while 90 joules of work is done to the system, how does the internal energy for the system change? This question is a direct application of the equation that change in internal energy is equal to heat plus work. The problem tells us that the system releases 180 joules of heat. So that means that heat is going from the system into the surroundings. Q is going to be negative 180 joules. Further, we're told that work is done to the system by the surroundings. So work is equal to plus 90 joules. Now that we've figured out the signs that are associated with heat and work, we can go ahead and plug it into our equation. 180 joules plus 90 joules is equal to negative 90 joules. This means that the internal energy decreases by 90 joules, and the correct answer is D. With that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.